Hello, welcome to Boom Incorporated. Our team is made up of Alexia Ochoa Hernandez, Connor Hansen, Marinata Beferdu, Mark Orlando, and Jacob Martinez. We are committed to making a cost-effective and readily available device that not only prevents pressure ulcer formation, but also provides relief for patients already experiencing symptoms.
Pressure ulcers, also known as pressure sores or pressure injuries, they are caused by prolonged pressure of bony prominences against the skin. Areas most affected include the sacrum and coccyx. Severity is categorized into four stages. Pressure ulcers are directly related to hospital length of stay and patient immobility. 60,000 deaths out of 2.5 million hospitalized patients are related to late-stage pressure ulcers. The growing elderly population in America has placed an increased demands on healthcare providers, many of whom are responsible to mobilize their patients themselves.
Our solution is a modular inflatable device that is made up of four separate cells. The first two cells cover the entire back and are separated into the left and right sides. The last two cells are on the upper thigh. The device works by inflating the inflatables on the left or right side while the other side is deflated to relieve pressure. The inflatables are connected to an air compressor via plastic tubes and a valve. The compressor is also connected to a control unit that monitors the pressure distribution and allows for rapid emergency deflation in cases where the patient needs CPR.
Throughout this project, we have performed various quantitative and qualitative tasks that resulted in our final concept prototype. This process includes concept generation practices and understanding the needs through clinical mentors. Completion of this process identified 5 main needs metrics that our device must address to efficiently prevent pressure ulcer development. From these metrics, our team was able to create technical models to validate the design of our device to address the customer needs. The following equations were used to resemble these models. The first model on the left exemplifies pressure distribution of the patient on our device. The contact pressure of the patient must maintain a level under 32 millimeters of mercury, as this is capillary pressure. Different heights of the air cells were tested in order to gain insight into the behavior of the contact pressure on the device. The final results revealed the device's success in reducing overall contact pressure.
We also modeled the rate at which we could completely deflate the air cells based on the pressure induced by the patient, ranging from 70 to 300 pounds. This is important because the patient needs to be on a firm, flat surface for CPR to be administered in the case that it is required. Our initial models show complete deflation capability in less than half a second for both cases, making our device CPR compatible. Our future directions include the ordering of required materials and their assembly to create a physical prototype, and the testing and validation of our product components, including material properties, airflow, and biocompatibility. We also need to stay diligent in our design considerations to keep our device within FDA and ISO standards to ensure a marketable product, as well as continuing our outreach for consumer feedback through survey expansion.
The team would like to thank our faculty mentor, Brett Vernon, our technical mentor, Chris Leasing, the wound care at Honor Health, and the BME upper management. If you have any further questions, please feel free to reach out. Thank you.